Okay, now we'll go through the calculus revision test. First of all, there's a limit question. From first principles, find the slope function. So this is the slope at all points. And the formula we use is f dash x equals the limit as h tends to 0 of this here. I'll just remind you where that comes from. It comes from a function f of x, and we are moving this point towards the other point, and we're finding the slope at that point there. That's an instantaneous slope, and these coordinates, this here is x, and this is a little bit to the right, x plus h, and that's why we're moving h to 0, because we're moving that second point towards the first point. And this here is actually the slope, because the coordinate of this point is x plus h, comma f of x plus h, and the coordinate of the first point is x, comma f of x. So we do y2 take y1 on x2 take x1, we will get this. This is the average slope. But when we move h to 0, in other words move the second point to the first point, we are then getting the instantaneous slope, which is the slope of this tangent here at that first point. So plugging into the function here, we're going to plug in x plus h. So it's x plus h squared. 4 times x plus h, take 5. That is f of x plus h there. Then we subtract off f of x, and all divided by h, because the x's cancel out. Then we need to FOIL this one here. So there's first, outers, inners, last, done there. Expand this bracket out, 4x and 4h, and multiply this minus through into that bracket. So it's minus x squared plus 4x plus 5. Then things start cancelling out. We have x squared cancelling with x squared, and the 4x's go, and we'll come down to this on the numerator. We can take out a common factor of h, and that's what we want to do, because we need to cancel that bottom h, because if you put h as 0, it'll be undefined. But now that it's cancelled, we can put h as 0, and so we get 2x take 4. Next question is draw sign diagrams for f of x and f dash. Now fx is here, but to do a sign diagram we need to have it in factorised form so we know where the zeros are. So factorising that, we will have this here, that's doing 4 in reverse, and so the zeros are 1 and minus 5. Minus 1 and 5, the opposite of these numbers. So the solid lines are where it's 0, where the y coordinate 0, and you substitute numbers in, you can get plus, minus, plus. The derivative, you can't get the derivative from this factorised form, you have to get it from this form up here. So it's 2x minus 4, with the number at the top coming down the front, and looking up at the simple derivative rules, you'll be able to get 2x take 4. Now 2x take 4, the 0 of that is 2, because 2 2's are 4, 4 take 4 is 0. So solid line over 2, and if you put numbers less than and greater than 2, you'll be able to get minus, plus. Now can you use the sign diagram to explain when f of x is decreasing? Well, f is decreasing when f dash is negative, and f dash is negative in this region here when x is less than 2. So that's what this says here. And that's all we need to do. It's got a picture here of f of x, just explaining why it's decreasing. We can see it's coming down here, and that's the decreasing part. So when x is less than 2, it is decreasing. After that, it starts increasing. But we got that from the f dash sign diagram. We didn't have to interpret it in terms of its function graph. Question 2, we have a a rational function here, point A and point B, and the first question is to find the slope of AB. So this is the average slope between A and B. It's not an instantaneous slope. So we use y2 take y1 and x2 take x1. So this is y2 take y1 and x2 take x1. And so that's this here. If you continue working with that, with the fractions, you end up with a third. So because it's an average slope, we say the average rate of increase in expansion of space, because the context of this question is that it represents the expansion of space after the Big Bang. So the if that's the expansion of space, then the slope, which is the rate of change, is the rate of increase in expansion of space from 1 second to 3 seconds, because we're doing it from 1 to 3, and we're working out how quickly that changes, or the rate of increase. And so the answer is a third, but the units would be units per second, because we don't know what it's measured in. It says here that it's measured in units. We don't know whether it's kilometres or what other sort of length measurement. Find from first principles f-3. This is now working out an instantaneous slope. This here was an average slope. This is an instantaneous slope at a single point. So to do that, we use our limits. The limit as x tends to 3, because it tells us to do that from first principles, which means limit. And we do y2 take y1 on x2 take x1. This is where we've got the function. In this case, if we look at the function there, it's bending like this. And so this point here is 3, f of 3. But we make up a point over here, x, f of x. And so what we do is we send this second point towards the first point. And so the average slope starts, then becomes the instantaneous slope at that single point. So there's f of x, there's f of 3, so that's y2 take y1 on x2 take x1. Clean all that up, and you get all the way down to 1 on 9. Notice we have to cancel that x take 3 factor out from the bottom, otherwise we get undefined. And so there's a little bit of fraction manipulation going on here. You should be able to work out what we're doing. Here we've got 1/3 take 1 on x. I'm getting as a common denominator is 3x, so I'm actually timesing the top by x, times the bottom by x, times the top by 3, times the bottom by 3. And then I get that one there. When you divide a fraction by a number or something like that, that will go into the denominator, and then these cancel off, so it's 1 on 3x. Put in 3 and you get 1 on 9. So that's the instantaneous slope at that point. Interpret the value of that, so it's the instantaneous slope or rate of expansion in space, because it's at t equals 3 seconds after the Big Bang, and so it's 1/9 units per second. Okay, now the simple differential rules. 5 comes out the front, making 10, take 1 off the power, 3 out the front, take 1 off the power, minus 4 out the front, take 1 off the power. This one here you need to simplify first, so we combine 1.5 to get 1.5. You add indices, powers, and when you multiply the bases, and now we do the derivative. So this comes out the front, multiply by 8, and you take 1 off the power. This one here, power out the front, take 1 off. Derivative of a number is 0, and this one here, power out the front, take 1 off. Now some context questions, problem solving. So this here represents the equation of the land. This is the land here, the shape of the land, and find where the lake is located. So we want to find that x-intercept and that x-intercept. So it's clearly going to be 2 and 3, and the other one's 0, so there's 3 x-intercepts, but the lake x-intercepts represent 2 and 3. So that's there, it's in kilometres. Part B, find where the derivative, find the derivative, interpret its value at 1/2 and 1.5. So if that's 2 and that's 3, it looks like 1/2 is about there and 1.5 is about there. So they're asking us to find the slope at that point and the slope at that point, because they're asking for dy dx. So to do that, we need to write the function down and first of all put it in power form ready for the derivative. So we're going to expand the x through, and so we get a cubic, and now we can do the derivative. I've left the 1/10 out the front because that doesn't affect the derivative, we just keep it there, and we do the derivative of this bracket. So 3 out the front, take 1 off the power, 2 out the front, take 1 off the power, 1 out the front, take 1 off the power. That's our derivative. Now we want to work it out at 1/2 and 1.5. So we plug in 1/2 where x is, so x becomes 1/2, x becomes 1/2, and so we get 0.175. Likewise, if we plug in 1.5, we'll get this value, minus 0.225. Now the meaning is that it's rate of change in height, rate of change in vertical height with respect to horizontal distance. So it's really a slope value. It's really unitless because this is in meters and that's in meters, so it'll be meters per meters, which is no units whatsoever. Actually, it's in kilometers, so kilometers per kilometer. Okay, 5. Now we've got a motion particle. We're going to do motion diagram for this. So draw sign diagrams for the velocity and acceleration. That's the function, that's the distance function. To get the velocity, we need to do the derivative. So this is distance, that is velocity, and this is acceleration. So do the derivative of that, we get this, factorise it, take out a common factor first, then FOIL it. Then we can do the sign diagram, cutting at 2 and 4. Likewise, we continue on to the acceleration. So we're going to do the derivative of this, and we get that, and then factorise it, take out a common factor, do the sign diagram, 0 at 3, and get the signs. Then the next question is find when it reverses direction. So it reverses direction when the speed is 0, velocity is 0. This is the velocity sign diagram, so it's when this is 0. So it's this time and this time, time 2 and 4 seconds. So 2 and 4 seconds, we need to know the distances. So we do what's the distance at 2, the distance at 4. Also know where it starts, the distance at 0 seconds. If you plug them into the top function, then you get 20 meters, 16 meters, and 0 meters. So the motion diagram, it starts at 0, it goes to 20, comes back to 16, and then goes on. You can also get that from the velocity sign diagram, which says it goes right, then left, then right. So down here, it goes right, then left, then right. Next question is, when is the speed decreasing and when is the velocity decreasing? Now you got two rules. Speed's decreasing when A and V have opposite signs. Now they have opposite signs. If you look up here, when this here is positive and this will be negative, then we could say that they're opposite. So when t is less than 2. The other time they're opposite is in this region here, in between 3 and 4. So it's negative and positive, but the other regions, they're the same. So less than 2 and in between 3 and 4, which is what this says, less than 2 and in between 3 and 4. Now that's speed, but velocity is different. Velocity is decreasing when, because that there is a function, velocity is decreasing when its derivative is negative. So when the acceleration is negative. And so you just look at the acceleration diagram there, and that's negative when t is less than 3. So when t is less than 3. Now that rule, that second one there, for velocity, this rule basically is, this holds for anything. If any function is decreasing, means the derivative of the function is negative. That's the concept we're using in this question here. The other question is related to speed. Now speed, we don't use that because we don't have the speed function. It's actually the velocity function, so that's not a function. We have to use this rule, linking acceleration and velocity signs together. Now part D is find the total distance in the first 5 seconds. We don't know where it is after 5 seconds, so we put 5 in for the distance function, and we now know it's at 20. So now we know the total distance is, it goes 20, back 4, and then up another 4. So this is the, up on the top diagram is like this. It goes to 20, back 4, another 4, and that's it. So 28 meters in total.